beam problem in order to calculate the displacements and also to plot shear force and bending moment diagrams using ANSYS software for a cantilever beam. And also I will try to cover a different kind of problem with different varying loads, uniformly distributed load or varying loads as well. Okay, now first we will solve this problem and we will discuss how to solve this problem in the later part of the video. Okay, right. Now this is our first problem. Let us quickly solve this problem. Go to ANSYS. The first step is change the title and enter the title as beam problem. Click OK and select the fit view option. Now go to preferences, select the structural. Go to preprocessor, element type, add, and for the beam problem we have to select beam 2 node 188. Beam 2 node 188. Click OK. Close. Now go to material properties, material models, structural, linear, elastic, isotropic, and we have to enter the Young's modulus here. For this problem, the units are in lbs and feet, but the Young's modulus is given in GPa. It is one of the most important parameter that all the units follow same system, either MKS, CGS, whatever it may be. All the units must be in one format. So convert this GPa to lb into feet. So for which here I have the formula. 1 GPa is equal to 0.145 into 10 power 6 psi, and further psi is converted to feet square by using this. So I am using a calculator. It is 200 GPa, 200 into 0.145 into 0 into 144. That is 4032 into 10 power 6. Okay. Now enter the value here. It is 4032 is 6. It is not necessary to give the Poisson's ratio in beam problem as well, for which I am entering the value as 0.3. Click OK. Close. Okay. After giving the Young's modulus value, the next step is go to sections. Click on beam common sections. Beam common sections. Here we have lot of predefined sections. For example, if we have a circular section, we have to give the radius value. If we have a rectangular section, we have to define B and H values. For the problem, they are defined as 0.25 and 0.25. Based on these dimensions, it will calculate the moment of inertia and other necessary parameters. What is the area, what are the moment of inertia, etc. It will calculate. Okay. Click OK. Again, now go to modeling, create key points. In active coordinate system, the first key point at 0, 0, 0 and the second key point at minus 3 feet. So in active coordinate system, the second key point at minus 3. Click OK. Now join with the help of lines. Click OK and go to meshing, size controls, manual size, lines, all lines, and I am making as 100 elements. Click OK. Now go to mesh, lines, this, click OK. Now it is completely meshed. Now apply the boundary conditions. For this problem, it is a cantilever type problem, and one end is fixed and the other end is having a point load. Okay, so go to solution, define loads, apply structural displacement on key points, and at this point we have all DOF to be arrested, and force key points. At this key point we have a downward direction force of 5 lb. So the value is, in the y direction, the value is -5. Click OK. So this end is arrested and this end the load is applied. Now go to solve the current LS. Click OK. Close. Now go to general post processor, deformed shape, deformed plus undeformed, and select OK. This is the displacement value. If we want to see the animation here, go to plot controls, animate deformed shape, deformed plus undeformed. So because of the applied loading, this is the maximum deflection we will get. So this is animating both forward and backward direction. Select the option forward only. So only in one direction the structure behavior can be seen in the animation. So click on stop and close. So this is the displacement. Okay. Now if we would like to see the shear force and bending moment diagrams, we have to create the element table. Before element table, go to read results, click on previous set or last set. We have another option also, type set comma all here, set comma all here and plus enter. Okay. Now go to element table, define table, select add, go to by sequence number SMISC 3, apply, SMISC 16, apply, SMISC 6, apply, and select 19. So 3, 6, 16, 19. Okay. Click OK. Out of which the first two parameters will indicate the bending moment diagram and the other two will give you the shear force diagram. Okay. Now click on close. Now I would like to plot the shear force diagram. So for plotting, go to plot results. On contour plot, select line element results. Select line element results. In the line element results, select the combination of 3 and 16. Click OK. This is the bending moment diagram. And click line element results and select the combination of 6 at node I and 19 at node J in order to get the shear force diagram. So bending moment diagram, the combinations are 3, 16, and for shear force diagram, the combinations are 6 and 19. So you have a doubt that, sir, how we have to remember all these parameters? No need. Go to the element type. Which element you have selected? Beam 188. Now type here help, comma, beam 188. Press enter. Help comma beam 188. It is asking for another window in related to the ANSYS material library. ANSYS material library. Here we have the beam 188 element description. It describes the properties of beam 188. So you can study at your free time what are the basic elemental properties, what is the length, what is EI flexural rigidity, and all the other parameters related to beam 188 we have here. It is the help. Similarly, you can also check for the truss element, the spring element, everything. Why we are considering that particular element to that particular problem is also defined in the theory part. Okay. Here, if you check at the element table definition, yes, here we can see moment in Z direction. We have to enter SMISC 3 and 16. The shear force, we have to enter the SMISC and 6, 19. For this reason only we have given or we have specified the values as SMISC 3 and 16 for bending moment and 6 and 19 for shear force. Okay. You have a doubt. Sir, for example, if I have a different kind of loading, what you have to do? If you have different kind of loading, so where we are applying the loads? In the solution phase, defining the loads. Apply structural. Here we have an option pressure. We have an option pressure. Select the item pressure on beams. Pressure on beams. I am selecting few components. Click OK. If it is a uniformly distributed load, enter the pressure value at node I and leave the node J value. If it is uniformly varying load, enter the first value here, the second value here. Be ensured that it should follow the plus and minus symbols as well. Similarly, if we have the other kind of forces, for example, I am selecting this and selecting OK. Here we have, apart from the regular standard forces, we have the moments as well. By selecting the corresponding moment, you can enter this value and you can click on apply. Likewise, all the displacements, forces and pressures are given in the solution phase, and in the preprocessor phase we enter the sections, common sections. Here we have more number of sections. On selecting this, we will give the parameters described in the figure. Width 1, width 2, width 3 and thickness 1, thickness 2, thickness 3. So on giving these values, it automatically calculates the moment of inertia, and the combination of E and I it will calculate, use in the formulas in order to display the required results. Okay. So this is also a very important model in case of beam problems. So the difference is element type. We have to select the corresponding element as beam 188, and we miss generally entering the values and sections. Based on the section, we have to give the input data, modeling, meshing, and in the loads section, displacement, force, if it is uniformly distributed load or uniformly varying load, you have to enter that values in pressure on beams, selecting the beam and giving the corresponding values. Okay. I hope with this you can understand the beam problem. Okay. Let us say this problem. So we model this component, and this is one key point, this is another key point, this is another key point, and this is another key point. These two key points are joined by a line. These two key points will join by a line, and these two key points will join by a line. After meshing at this point and at this point, we arrest the degrees of freedom, and at this point we apply the force, and at this point we apply the force, and throughout this length we apply the pressure on beams and enter a constant value of 1.5. Okay, right. Try to solve this problem. Okay. Thank you.